Great, thank you, John. I think John provided a nice prologue to the topic that I'm going to talk about, which shifts gears a little bit and focuses on the utilization of animals to better characterize and understand the health hazard of inhaled diesel exhaust. And what I'm going to do today is give you a little bit of an update on the Advanced Collaborative Emission Study, at least phase 3 of that work, which is managed through under a contract with the Health Effects Institute to look at the toxicity of inhaled diesel exhaust in rats and mice. And those studies are underway, but I'm going to give you an interim report on the results from that and provide you some information that's going to be published by HEI sometime in April. But I'm also going to provide you with a little bit of additional background that sets the stage for some of the work that's been conducted over the past several decades to better characterize the health hazards of diesel exhaust using animals, of course, which is one of the species that you can use, obviously. So, for some historical perspective, we've been looking, we as a scientific community, have been trying to understand and better characterize the health hazards associated with inhaled diesel exhaust since the 1950s. Diesel exhaust, as we've known it, has provided emissions that have a ubiquitous exposure, and because of the composition and complexity of the emissions and the number of chemicals that are emitted, especially in the older technology, there's plausible human hazards from the emissions that have come from older technology in particular. The diesel exhaust research, especially within the health community, engineers have been studying it from long before the 70s, has been a tremendous focus, especially starting in the 70s, even though the work started in the 50s. A lot of this started from some, as I'll mention in a little bit, some findings associated with the mutagenicity of diesel exhaust in the early 70s that led to a lot of research and concern over the potential carcinogenicity of inhaled diesel exhaust. Within the health research community, those initial findings related to the mutagenicity of diesel exhaust focused a large microscope under diesel exhaust, but there was really limited parallel attention within the health research community on gasoline engine exhaust. Our organization, for example, has almost 150 publications on the health effects of diesel exhaust and maybe 5 publications on gasoline engine emissions. And we're one of the top organizations in studying the health hazards of gasoline engine emissions. And so that gives you just a little bit of context in the relative emphasis on diesel versus gasoline. There's, within the health community, just to characterize the types of people who are providing information to better characterize and understand the health effects of diesel exhaust or engine emissions in particular, and in fact environmental pollutants. In general, there's been a less of an emphasis among an understanding of the emissions among health researchers. And this is displayed in the literature when you look at a lot of health studies where biological results are reported, but in many cases the composition or type of emissions are not characterized or not defined. And in some cases this has made it difficult to interpret that literature. I'm not focusing on epidemiology studies or studies involving humans today, which of course is the most relevant species for understanding health hazards to humans. But it is noteworthy that the epidemiology studies in the database has shown associations with a number of health effects with occupations where diesel exhaust exposure is plausible. The majority of that literature is tempered because of the limited or poor documentation of the actual exposures. Usually a lot of the associations are based on job function or duties, and a lot of times we don't know exact exposures when you're recreating the potential health effects of that diesel exhaust, which makes it difficult in some cases to best associate health effects in those populations. The animal studies, which are used to inform our understanding of animal studies and inform how we go about and interpret and regulate and associate the risk associated with any materials. In the diesel exhaust context, they started in the late 70s, early 80s, looking at health hazards and cancer associated with inhaled diesel exhaust. And they found that diesel exhaust indeed caused cancer in laboratory rats. But a decade long of additional research looking at cancer in rats and in a number of other laboratory animal species tempered the enthusiasm and the interpretation of those results, and suggesting that the cancer that was found in the rats may be specific to that particular species and may not be due to the fact that it was diesel exhaust and to carcinogenic material in diesel exhaust, but rather to the effects of an overwhelming dose that was achieved of particulate material that may be not selective or not specific towards diesel exhaust in particular. I'll give you an example of that later on. So that led to the EPA in particular recently in their evaluation of health hazard of diesel exhaust to temper their emphasis on the utilization of laboratory animals and looking at the cancer hazard of inhaled diesel exhaust. Of course, while cancer is a driver for a lot of the risk assessment associated with diesel, there's a lot of non-cancer effects, inflammation, and a range of cardiovascular and other effects that have been documented both in laboratory animal studies in our lab and others, as well as controlled effects in humans as well and occupational studies. The majority, in fact almost all, of the research database that's on diesel exhaust, of course, is based on technology that is prior to 2007. Certainly all of the research in humans and the majority of it in animals. In fact, very little has been studied until recently on new technology and its impact on the potential change in the health response to inhaled materials. So looking back at where the cancer hazard in particular for diesel exhaust started in terms of it getting attention goes back to 1955 and early on, looking at taking solvent extracts of diesel and gasoline exhaust material and doing a mouse skin painting it on the skins of mice. And they found that when they took those extracts and painted that material onto the skins of mice, they did see increase in tumors on the mouse skin. They related that to source, operating condition, and the aromatic hydrocarbons content of those emissions. What really started a flurry of research, as I mentioned earlier, in the 70s when they found that within the Ames mutagenicity assay, where you look at mutations in Salmonella bacteria, they found that diesel exhaust in particular had high potency towards causing mutations within Ames, which at the time was well utilized, and to this day is well utilized as an in vitro assessment of potential mutagenicity potential. A lot of work with diesel exhaust and doing studies using bio-directed fractionation pointed towards nitroaromatic compounds as being the important or putative compounds that was causing the mutagenicity in those extracts. And what bio-directed fractionation is you would take material, for example, you have a filter of material, you extract it, and then you want to find out if this material, that extract, causes some mutagenicity within that assay. If you wanted to know what component within that extract is actually causing that mutagenicity, what they would do is then separate it out and parse that out chemically and through chemical and physical separation until they were able to identify the extracts and then eventually the compounds that were causing the mutagenic response within that particular assay. And again, nitroaromatic compounds were identified as being the most important from diesel exhaust. So a lot of that work during the 1970s caused, again, a lot of interest in the potential cancer-causing potential of diesel exhaust. And so in the late 70s and early 80s, a number of large-scale rodent studies began. This occurred both in the US, Germany, Switzerland, and Japan. And studies were consistent across a number of studies that were conducted across the world. And in each of these, they found that especially at the highest doses of diluted exhaust, based on typically diluted down to high doses of particulate material, high concentrations of particulate matter, those high doses caused lung tumors in rats. They did not see the same increase in lung tumors in mice or Syrian hamsters. And as I mentioned earlier, and we'll get an example in a second, they associated this excess lung tumors in a specific species-specific relation to the particle overload that is occurring in those animals. An additional example of the mutagenicity studies that were conducted, these ones in particular at our laboratory, also identified the importance of understanding the differences in operating conditions within diesel engines or within any vehicle on both the composition, as we would understand, but also potentially the toxicity, in this case manifested by the Ames mutagenicity assay, where a study was published by Bechtel using a 1980 GM 5.7 liter certification fuel, etc., operating an engine on an FTP cycle and a driving cycle, and collecting different fractions of emissions during that cycle, and finding that you had different amounts of mutagenicity depending on the component of that cycle that was linked to differences in composition. John covered that topic. So the mutagenicity was one point, and again, what led to a lot of the interest was the results from these rat studies that showed a dose-dependent increase in tumor burden for rats exposed 7 hours a day, 5 days a week, for a lifespan study in a rodent, which is about 30 months, to whole diesel exhaust. Whole means you capture both the gas phase and the particle phase, and they're living within chambers that they're exposed to. And as you can see, where that x-axis here is soot concentration times time, or the amount of time that they're exposed on the x-axis, and on the y-axis is the percent increase in tumor incidence. As you can see, there was a dose-dependent increase. And what occurred with these particular studies and these data was that there was a projection of the lowest dose, because we had a linear response through these data, to projecting that potentially that tumor burden or that tumors or cancer could occur at lower concentrations, much below the concentration shown here that provided excess tumor burden. But if you looked at the lower concentrations that were evaluated during those studies, and these studies were evaluated with a high number of animals to enhance the probability of detecting a potential excess tumor burden, what they found was that there was not an increase in tumor in rats at the lower doses that were evaluated, suggesting, because of the way that these studies were powered, that the lower doses may not be able to be adequately extrapolated from the higher doses to predict an excess in potential for cancer. The other interesting component of the story was the notion that they wanted to understand more in these studies that were conducted about the potential for the mutagenic components of diesel exhaust, these things that were identified in particular in Ames assays as being mutagenic. Wanted to understand the role of the organic carbon fraction in causing the cancer and the excess tumors that were identified. And so a series of studies were conducted to try and understand that potential role. And the way that they conducted those studies was to look at carbon black, or material that was void or deficient in organic carbon, and compare that to diesel exhaust and other types of material in different laboratories at the same particulate matter concentration and over lifetime studies. And what they found was that the same types of exposures that at different particle concentrations, that the dose response, if you look here at the x-axis, which is the same cumulative exposure dose response type of x-axis that I was showing in the prior slide, and then the y-axis again, looking at excess lung tumors. As you can see, if you look here up in the far corner, these are Printex 90 and titanium. These are different types of particulate materials, non-diesel exhaust, at those concentrations, those doses. And they looked at diesel soot as well as looking at carbon black, and they found that you could superimpose almost the dose of particulate matter with the percent increase in tumor burden. And so when I was first learning of this story, the notion was that this, because this is potentially a non-specific response, is not addressed through a mutagenic mechanism, it's not related to the organic carbon fraction of diesel exhaust, you could grind up this carpet or this podium here, and potentially, if you got it into a sufficiently small size to aerosolize it and be inhaled by rats at the same concentration and same dose, that it would likely cause the same tumor burden as diesel exhaust did. And so it was considered a very non-specific effect that was seen in rats. And again, they did not see the same type of excess cancer burden in mice or hamsters. And that's what it led to, unfortunately, or the way it is, a tempering of our ability to utilize these data to better understand the health hazard associated with cancer in humans. So I'm going to shift gears now and talk about the Advanced Collaborative Emission study. Again, this study is conducted under contract by our laboratory, Lovelace Respiratory Research Institute. This phase of the study is phase 3B, managed by Health Effects Institute, funded by a combination of government and industry. And the focus of these series of studies is to better understand both the toxicity and eventually the carcinogenicity potential of 2007 compliant diesel exhaust. That's the study that's undergoing right now. The study started off, like any study, with a null hypothesis. And that hypothesis written here was that the emissions will have very low pollutant levels and will not cause an increase in tumor formation or substantial toxic effects in rats or mice at the highest concentration of exhaust that can be used, compared with animals exposed to clean air, although some biological effects may occur. The study design was not developed by Lovelace. It was developed by a consortium that was managed by the Health Effects Institute, and it was vetted through an external advisory panel. The design was based in large part, especially for the carcinogenicity component, on the cancer design for studies conducted by the National Toxicology Program, where you're looking at cancer as an endpoint, but utilizing a number of biological endpoints that are well vetted through the National Toxicology Program. And again, similar to studies that are conducted by the National Toxicology Program, the design of the study was developed such that you would have effects at biological responses at the highest effect level, and that the potentially, depending on the outcome of the study, you may then go down to lower effects levels to potentially identify a no observable effect level, as well as a level at the highest level that would cause a biological response. That was the design of the study. The core study design was a bioassay, which bioassay in this context means a lifetime study conducted in the Wistar-Hahn rat. The Wistar-Hahn rat was selected because of its low background and especially lung tumor incidence. The rat was selected at the animal doses looked at here, and also the animal numbers. The animal numbers were selected to be able to see a statistically significant increase of at least a 5% increase in tumor burden in terms of the animal numbers that were evaluated. An exposure paradigm, looking at 16 hours a day of exposure, 5 days a week for up to 30 months, depending on the survivability of the animals, was developed. 3 dilutions of whole emissions, the high emissions set at a level that was known or believed to cause a biological response, and clean air controls were evaluated, and 166 per group were evaluated for the carcinogenicity assay, and then other animals were selected to be looked at interim sacrifice points. In addition to the cancer endpoints, additional biological responses were looked at for respiratory function at 3, 12, and 24 months, lung lavage, or when you wash out the lung with a saline solution to be able to look at increases in proteins and inflammatory cells and things like that. Lung tissue, or looking at lung tissue both under a microscope by a trained pathologist to understand and see if there's any tissue changes or tissue remodeling or tissue injury, as well as biochemical assays within lung tissue to understand if there's increases inflammation or proteins that might tell us something about what's going on in the lung. Hematology and serum chemistry in blood to look at potential effects in systemic inflammatory or toxic responses that could occur. And then again, histopathology that was used to look at the lung tissue response. The bioscreening study in mice, which was a parallel activity, was occurred, and the mouse studies were conducted to better understand species comparisons between rats and mice in terms of their sensitivity to this particular types of atmosphere, as well as to enable some ancillary studies that were conducted under separate contracts by the Health Effects Institute to look at some non-standard biological response assays, and I'm not going to talk about those today. In this particular study, it was up to 13 weeks, 120 mice per group, exposed to the same protocol. Many of the same biological response indicators were looked at up to 3 months. That is in parallel to the ancillary studies that were conducted in these mice. The exhaust generation, the system, these studies are unique relative to many of the diesel exhaust studies that have been conducted in the past, in that typically the diesel engine facilities have been a lower horsepower, lower types of energy output. This is a larger engine. It was rated up to a 600 horsepower engine facility. The engine is operating on an alternating current dynamometer through a specially designed cycle that was designed for the program to be a very aggressive cycle that incorporates a number of different modes that would really test the bounds of the rigor of the engine, as well as the rigor of the engine after treatment ability to maintain the emissions reduction that it was originally designed for. And this is conducted, again, on a very aggressive cycle, 16 hours a day, 5 days a week. I guarantee that in John's lab, he's never run an engine that long under these types of cycles. And it's a very impressive feat to be able to ensure that these systems can be running for 5 days a week, 16 hours a day, not because of the stability of their system, but these are very complicated, integrated systems that we're maintaining, and we've had a lot of success in doing that. The exhaust is diluted after going through the DPF in the standard after treatment system. That goes into a dilution system that you can see here. I'll see if I can use this pointer here. It goes up here into the primary dilution system here. This is where the engine exhaust goes up into the dilution system. That dilution system, then the emissions are routed here into a laboratory that is immediately adjacent to the engine control laboratory. Within that laboratory, you have a engine exhaust takeoff point. And this picture on the lower left-hand side is looking within the dilution tunnel, and those are the ports, the probes that are in line with the exhaust as it's flowing down the tunnel. And each one of those are different size ports for the different amount of exhaust that would need to be extracted for each of the different exposure levels. The top left-hand picture is an outer schematic of where the probes go into the dilution tunnel to extract the exhaust. The air is extracted, and then as you can see on the right-hand side schematic, it goes through a muffler to dampen the sound. There's additional dilution steps in what we call dump, or a bypass of air to balance flow within the chambers. And then the final dilution of material goes into the exposure chamber here, and the animals live within this chamber. It's a flow-through chamber. This is a 2 cubic meter size chamber. The animals spend their lifetime within this chamber, within caging. They're allowed free access to water and food during that time. There's multiple chambers for each level, and the caging for each level are modified to ensure that the animals have adequate space during their lifestyle and during their lifespan as they grow. So I mentioned several times earlier that the exposure concentrations were set at a level that would, at a dilution level at the highest level, that would likely ensure a biological response. And that was ensured by the study design based on the historical data on the effects of NOx on lung and other effects. And so the highest concentration was, and all of the concentrations were defined based on the dilution indicator of NO2. And utilizing NO2 as a dilution indicator for each of the different exposure levels, we would then characterize the rest of the composition of the emissions as they existed at those dilutions. The highest exposure target for NO2 is 4.2 ppm, followed by 0.8 and 0.1 ppm for the NO2 concentrations. The concentrations of other constituents of the atmosphere then trended or tracked as they did and as we characterized. These are the concentrations, the average exposure concentrations up through 12 months, which is the data, which is the longest duration of exposure for the data that I'm presenting today. As you can see, the concentration of NO2 is just looking at the high exposure level at a target of 4.2 ppm. You have about 5.8 ppm of NO. Just for context, one of the main contrasts in the composition of the emissions as we see it, in addition to the reduced particulate matter and things like that, the NOx from all of our older studies, in the majority of older studies in the literature, if you look at NOx, typically the average integrated NOx over a duty cycle was about 90% NO and about 10% NO2. So for these studies here, it's more, 60-40 or so. So as a proportion of the exhaust, especially for this 2007 compliant emissions, there was an increase in the amount of NO2. This is carbon monoxide, hydrocarbon, SO2, sorry, the units there are part per billion for the SO2. The particulate matter, as John mentioned earlier, one of the challenges is in measuring the particulate matter that come from the exhaust here. And we had those same challenges. And so one of the things we had to do, because of the dander and background that comes from having a large population within a confined space, there is a natural background of particulate matter within the exposure chambers that the animals exist in. That background is typically about 25 to 30 micrograms per cubic meter of particulate matter that's associated primarily with dander. And so what we had to do to better associate the concentrations that were directly related to the diesel exhaust was to actually take samples, if you have a chamber, to take samples immediately prior to the exposure chamber, prior to it entering into the chamber itself, so that we could better understand the contribution of diesel exhaust to the particulate matter. And we did a series of studies prior to putting animals into the chamber to verify that we could measure immediately prior to the chamber and then what's in the chamber, and that those results would agree in terms of our ability to represent what the animals were exposed to. And so that's why I report data in terms of the chamber inlet at 9 micrograms per cubic meter at the high exposure level, and that's compared to about 30 micrograms per cubic meter that's in the chamber that results primarily, again, from background. Just for reference here, so this is 9 micrograms per cubic meter at this dilution. Some of the higher concentrations for the older diesel studies that we're referencing earlier that were used for some of those earlier cancer studies, those were on the order of between 5 and 10 milligrams per cubic meter, or 5 and 10,000 micrograms per cubic meter. So a substantial difference in not only the amount of particulate matter that was in these atmospheres relative to those studies, but also, as John pointed out earlier, in the composition of those emissions. As John mentioned, the interesting, perhaps the most interesting part from an atmosphere perspective in these exposure chambers occurs during the regeneration of the diesel particle trap. And so what I'm showing you here are two figures that represent real-time particle mass on the top figure and real-time particle number on the bottom figure. For the top figure, that arrow from side to side represents one 16-hour exposure duration. Typically what we have during one 16-hour exposure period operating on this duty cycle are 2 regenerations of that trap. When that trap regeneration occurs, we see both a change in the composition of the gas phase, the NO to NO2 burden, as you would imagine, because NO2 is utilized to help regenerate the trap. We also see at that point an increase in the particle mass and particle number that come from the trap as a result of that regeneration process. And so as you see here, it may be a little bit difficult to see in the back of the room, but just the peak particle mass concentration, it can go up to 100, 150 micrograms per cubic meter for a relatively short period of time. If you integrate the time during the exposure, so just for calibration, each of those regeneration events takes about 90 minutes, okay, 60 to 90 minutes. And during that regeneration period, the average particle concentration is about 50 micrograms per cubic meter. So during a few hours of that 16-hour cycle on each given day, the exposure concentration based on particle mass, which is one component of the whole exhaust that we're interested in, is about 50 micrograms per cubic meter. Particle number, which is represented on the bottom slide, and what we had to do with this particular slide, because of the nature of the software we're working with, is break down the two 8-hour periods within 16 hours in two separate slides. So what we're looking at on the bottom figure is the same information in general, but it's particle number instead of particle mass, and showing that during the majority of the time that you're looking at the particle number in that exposure chamber, you don't see anything. But during two events that we see for both particle number and mass, we do see a spike in number and mass because of the regeneration event that occurs. And this slide is meant to mostly tell you that the characterization that was conducted for these exposure atmospheres that will be published in the upcoming report that's going to be presented by HEI is been extensive. We measured hundreds of individual components to characterize the composition and magnitude of the material within these atmospheres, including semi-volatile PAH, nitro-PAH, et cetera, et cetera. It's always interesting to look at these atmospheres in the context of the total amount of material as it exists as a percentage. Oftentimes we look at material and emissions in different units, and sometimes that can be, I don't know if misleading because we're used to looking at it in that way, but if you put things on the same units, you'll note that not only for modern technology diesel exhaust, but also older technology diesel exhaust, the majority of the emissions are of course CO2 and water. After that it's mostly NOx and CO, and then particulate matter is a very small fraction, even in older technology diesel exhaust, but particularly here. And so if you look at that top figure on the top here, you see mostly gas phase, but among the small amount of particle mass that's there, if you look at the composition, you see a fair amount of, on the high side especially, see a fair amount of organic carbon, sulfate elements, etc. So the study was conducted and has conducted as defined in that table. And a number of biological responses, in addition to the characterization of the atmospheres, was evaluated, and these were evaluated using a statistical approach that was developed as part of a statistical working group, and that statistical approach was applied to evaluate the biological response relative to clean air controls and relative to trends within groups. The biological response indicators that, as a sort of natural manifestation of the protocols that are utilized to look at the toxicity within these types of protocols, like the National Toxicology Program utilizes, there's a number of measurements. Within hematology and serum chemistry, just as a natural part of the data that you get, there's a wide number of measurements that you make, which so it makes us sensitive to potential type 2 statistical errors for just potentially false positives, and we pay close attention to that. But the point of this is not to list off every biological endpoint, but to note that there are many within hematology and serum chemistry. Within lung lavage, we looked at a number of different protein and other indicators. Lung tissue, we looked at a lot of indicators of both inflammatory and potentially oxidative response. We also looked at respiratory function, which is somewhat of a non-standard assay relative to the National Toxicology Program studies. And we looked at pathology and tissue pathology as well as organ weights, etc. And the findings, just to preempt what I'm going to discuss, is that the majority of the analysis, the majority of those endpoints, those biological responses we looked at, really showed no difference between diesel exhaust and clean air control. The histopathology analysis did reveal mild to minimal, and those terms are pathology terms. Those are not my terms. Those are what pathology designates as the severity of the response. So those are mild to minimal exposure-related hyperplasia in the rats after 3 months of exposure that was not observed in the mice. This increased, the amount of hyperplasia increased at 12 months, but was still classified by a board-certified pathologist as well as peer review as being considered mild or minimal severity. The statistical significant findings were noted for several indicators of what we call pulmonary stress and inflammation in rats. In mice, there were much fewer findings in the mice. I'm going to note some of the findings in the rats, and all of it will be published in this publication coming up next month. Respiratory function or pulmonary function assessments in the rats shows slight differences in respiratory function in exposed rats compared with control after 3 months, as well as at 12 months of exposure for one of the particular endpoints. So there were several endpoints looking at protein and albumin in rats that at the highest exposure level we saw some increase. And this is shown in these top figures, and those were statistically significant. The total antioxidant capacity, as well as hemoxygenase, which is a stress response protein, shown in the lower two figures. The antioxidant capacity, if that goes down, that is showing an increase in oxidative stress. We saw an increase in that response at each of the exposure levels, except for the control. We saw an increase in hemoxygenase at the high exposure level as well as the mid. It appears to trend, but we did not see that at the low or the control. These are relatively mild but statistically significant increases for these response after 3 months of exposure. We measured a number of different respiratory function or respiratory responses in rats. We looked at respiratory function in a way that allowed us to look at a much larger number of animals than we had looked at in any of the previous studies that we had utilized. We had an N of 10 per gender, and we looked at both effects based on individual gender, and to the extent that it made sense and the data could be normalized, we also looked at pooled genders with males and females together when we felt there may not be a gender-specific response. We did observe a trend in a statistically significant trend in a decrease in lung diffusion capacity measured as, or is the lung's ability to take up oxygen, measured by the addition of a small amount of carbon monoxide to the lungs, and seeing how well that the lungs would take up that carbon monoxide when you extracted it out. And we found that there was indeed an apparent exposure-related trend in the decrease in this lung diffusion capacity. Again, then these data are shown here on the bottom right-hand side for the 3-month responses, and in that case I'm showing each of the genders, and in the top left-hand side I'm showing this is a pooled gender. And in both cases we saw a statistically significant trend, but if you look at the high exposure versus control alone, that was not statistically significant. And if you look at each gender on their own without being pooled, it was not statistically significant. So the pooling of the genders, which gave us an N of 20, was able to decrease the relative standard deviation and allow a statistically significant response to be observed. So that histopathology findings, where the pathologist would take slides of all the tissues in the rats and mice and look to see if there's any tissue injury. We did not. The pathologist did not observe any systemic tissue injury that is outside of the port of entry or in the nasal or in the lungs. They did see some tissue remodeling and changes within the nasal region as well as in the lungs as a result of these exposures. This is just a table of incidents at the 3 and 12 month studies. This is just indicating the number within 10 animals that were evaluated, the types of findings that were observed, and of those 10 animals that they looked at, how many out of the 10 where they saw this observation. Primarily what they were seeing is in the acinar region of the lung, which if you guys can imagine your grade school picture of the lung, you're coming down, you see the grapes and where the airways come down and kind of distend down into the air sacs and things like that, right when you're turning that corner into this what's called the acinar region of the lung. Sometimes pathologists argue whether it's periacinar or acinar. We'll just call it the same for us, for our sakes. And this is the area of the lung where we're seeing the tissue changes here for these particular studies, just for that description. And so we saw that in all of the animals, both at the 3-month and the 12-month. The note that it's not evaluated not yet is untrue relative to the accumulation of macrophages. The point is, actually, we did not see an accumulation of macrophages at the high level. We did see a note of fibrotic tissue. It's important to note the difference between fibrosis, which is an idiopathic disease, which is very severe, and the notation of fibrotic type tissue, which is a type of tissue remodeling, type of cell modification. So just to give a couple of pictures of this, looking at what we're looking at here, this is just pictures where we took lungs, stained them with a special type of stain, and then the pathologists had looked at these, and they noted here this area that we're pointing out with the arrows, which is what we call the alveolar duct region, that you see that, hopefully you can appreciate the thickening in that area of the stain, which is a thickening of tissue in that area relative to what you see in the control. And if you look a little bit closer, I think you can probably see that even better, where you see the thickening of the alveolar duct right there, what's called the septa, right where it's entering into the alveolar duct region. And if you look at 12 months, what we're finding is that at 3 months you see, I think, the start here of the top figure, where you see just at the initial part of this acinar region here, where the air is coming into that area, you'll see that the initial thickening of those airways. And if you look at 12 months, I think you can probably appreciate that thickening is extending on and growing in terms of its footprint within the acinar region. And we're continuing to see at the 12-month evaluation point this thickened septae with an increase in, at some point, these fibrous tissues that are remodeling. And we see in some cases, in a couple of animals, also tissue remodeling that is also showing changes in the tissue type, showing bronchialization or basically shift into cells that are cuboidal type cells that actually have cilia on them, so they look more like bronchiolar type cells as opposed to alveolar type cells. So we are seeing some tissue remodeling. And note again that these were observed in all of the animals at the high level, and that again, the severity score, where a pathologist will rank the relative severity of these findings on a scale of 0 basically to 4. The score of all of these was typically was almost in all cases a 1, and I think we saw maybe 1 or 2 findings where it may have been a 1 or a 2, but pretty much it was a 1 out of a 4 scale in terms of the severity of the findings. Again, defined by the pathologist as minimal to mild. So certainly both by study design as well as the observation that nitrogen dioxide is a large component of the emissions that we're looking at, coupled to the fact that nitrogen dioxide is a known toxicant, it's likely important to look at the potential for NO2 to be important in driving some of the biological responses that are observed. Essentially, when this particular study was designed, I mentioned earlier, it was designed on the notion that there would be biological responses at the high level, and that was developed based on prior studies on the toxicity of NO2, and the doses that were selected were based on NO2 studies that were conducted prior, where we observed in a prior study that moderately published in the late 80s, when F344 rats were exposed to just less than 10 ppm NO2, they looked at pulmonary function, histopath, some of the immune or inflammatory response indicators. They found that NO2, is parallel to this study in some ways, caused epithelial hyperplasia, thickening of walls of terminal bronchioles, inflammation, and oxidative stress. In that study, there was little effect on respiratory function. I do note that study, is my recollection, was not powered as well as this study was for the respiratory function measurement. The effects at 12 months for that study was not significantly different than at the 24 months, and this did not progress. Again, the NO2 doses for the 12-month study here for ACEs were selected to be nearly identical to that prior study on NO2. If you look at the concentration times time, the Martley study was about 17,000 ppm hours of NO2 exposure, as well as that's pretty close to what we saw in the ACEs study. In summary, the 2007 compliant diesel emissions are different. There's lower stuff, and coming out of the tailpipe. As a result of that, there's a difference in the complexity and the type of the emissions, and as a result, these studies show a difference in the composition of the atmospheres that are being studied for diesel exhaust relative to the historical literature in this area. They do have some interesting differences in the proportion of NO2, etc. The exposures up through a year produced mild to no response in the mice, and minimal inflammatory and tissue remodeling and respiratory function and changes in rats. I use that term minimal again, not for myself to classify the relative ranking of the responses, but because that was the clinical term used by the pathologist to define the relative tissue response in these animals. Again, the tissue response was considered minimal. The statistically significant findings were observed primarily at the high level, but we did see some at the lower levels, and it will be interesting to see. In the respiratory function effects, we observed trends. We saw those trends both at 3 months and at 12 months. The relative magnitude of those trends and the responses did not appear to progress between 3 and 12 months. They're reasonably consistent. And again, the remainder of the study is currently underway. The schedule, as we look at right now, we're scheduled for our 2-month sacrifice this spring. And then at that point, we'll look at respiratory function, a number of these other endpoints. The current plan, which is based on the survival curves and survivability of the animals, is to extend the animals out to 30 months based on their lifespan, and to look at 30-month time span, which will occur later on this in November. And we'll look at those for the potential for increase in cancer incidence as well as other endpoints. And a draft report on these results for the final report will be submitted next June. Obviously, I didn't do all of this, and these are the people who take the credit. A lot of technicians and technical support went into conducting this research and continues to do this on a daily basis.